So today we look at section 8.2, which just like section 8.1 involves hypothesis tests. And this one is just for a little bit different condition. So it turns out there are two methods of testing the mean. There's the p-value method. And that's the method that we are looking at. It is by far the most popular method in use today. So I'll say this is the most popular today. When you look at the book, you may see them mention this critical region method. This is the way it was always taught up until probably about the mid-90s or so, when we didn't have a graphing calculator or a way to get some of these students' t-values. We had to use a critical region method, but that is not covered today. That is not covered in Math 15 or Math 215. So when you see it in the book, you can just ignore it unless you want to know what it was like in the bad old days when I was learning it. You can look at that, but the p-value method is a better method, and as long as we have technology, we can use that. The reason I say it's better is because you're not limited to tables, which typically go in intervals of 0.05 or something like that. So everybody pretty much uses the p-value method today. So for tests of the mean, which is what we are working with, for tests of population mean mu, we use one of two sampling distributions for x bar. Well, we can use a standard normal distribution if sigma is known, and that was in section 8.1. That's what we just looked at. And this is our test statistic, or the z-score for the test statistic, which is what we used in 8.1. Now sometimes sigma will be known maybe from like a previous study or something like that, but usually it's not known. So what we're going to move to now is the student's t-distribution, and this is what we use if sigma is unknown. So this will be in section 8.2. Now 8.2, when you're working on this section's homework, occasionally they'll also give us one like this, where sigma is known. So when you're working on testing the mean, one of the big keys is looking to see, do we know sigma? If we do know sigma, if they give us sigma, we're going to use z-scores. If they don't give us sigma, then we're going to use t-scores. So we'll have this new test statistic, or we'll take the t-value of our test statistic, and then look what is going to happen. If we don't know sigma, we're going to use little s from the sample. So this is going to be a lot like chapter 7. 7.1 and 7.2 were just like this. So just kind of keep that in mind. When it comes to a hypothesis test for the mean, we have to look right away and see, do they give us sigma or not? And if they do, we're right here. We use a z-score. We use standard normal. If they don't give us sigma, we're going to use student's t. So in both cases, if we can assume that x has a normal distribution or is mound-shaped and symmetric, the book will sometimes say this. I'll make it really clear if I ask you. I'll say either x has a normal distribution or I just won't mention it. But if it does, if we know that we're sampling from a normal distribution, then of course any sample size will work. If you cannot assume this, then we use the sample size, same as always. N has to be greater than or equal to 30, same as before. And then the note here is, in this text, we use student's t-distribution whenever sigma is unknown. And that comes to when we are looking for the mean mu. So in 8.3, we look at proportions, and then it doesn't matter. But when we're looking for the mean and sigma is unknown, we're going to use student's t. And so with that, we are ready to try some of the problems. So we've got page 465, problem number 2. I want to ask this one because this one gets to an important idea for us. For problem number 2, it says to test the population mean mu for an X distribution that is mound-shaped using sample size n greater than or equal to 30. So we're all set, right? We're testing the mean mu. So we got some sort of hypothesis test. Sample size is greater than or equal to 30. So we just need to know, are we going to use the normal curve? Are we going to use standard normal distribution or student's t? So this is an important point that we just talked about. If sigma is known, use the standard normal distribution. In other words, use z-scores, right? Those are z-scores with a standard normal curve. And if sigma is not known, so they don't tell us, or they tell us that we don't know sigma, in that case, use student's t. Use the student's t distribution, and in other words, t-scores. So again, that's the important part in Chapter 8. When we are testing the mean, we've got a hypothesis test involving the mean. We have to look and see if we know sigma, and if we, in that case, we're going to use z-scores. If we don't know sigma, we're going to use t-scores. Okay, so that's important. Then number 4 says, consider a test for the population mean mu. If the p-value is such that you can reject h0 at the 5% level of significance, can you always reject h0 at the 1% level of significance? Well, the answer is no, of course, because just let's suppose the p-value equals 0.03. So if it's 0.03 and you would say, okay, so the p-value equals 0.03, right? And if we were going to compare that to 0.05, which is alpha, you'd say, well, the p-value is less than alpha, so that means we would reject the null hypothesis, right? We reject it. So at the 5% level of significance, we reject the null hypothesis. But what if we didn't have that? What if we had 1% level of significance? So then we say the p-value is 0.03, but in this case, alpha is 0.01. Let me just separate these a second here. So then we look, we say, okay, the p-value this time is greater than alpha. So in this case, we would say we would fail to reject h0. And I know the wording sometimes seems awkward, fail to reject. And students sometimes say, why don't we just say accept h0? And you can say that. The reason that wording is typically not used is because some people think it sounds too strong, like almost like you're proving that h0 is true. So we want it to come across as, we looked at the evidence is not strong enough to reject h0, so we're not rejecting it, we're failing to reject it. So that's kind of where the idea behind that wording. But this is just saying, with a p-value 0.03, and until we know what alpha is, we don't know what's going to happen here, right? We're going to get completely different results based on alpha, which is why in the conclusion we always have to say, we always start a conclusion off with at the 5% level of significance or at the 1% level of significance. So we always mention that in our conclusion because that's telling the reader the line in the sand we're using. And you can see if the p-value is 0.03, If we're using a 5% level of significance, well, we're going to reject the null hypothesis. If we're using a 1% level of significance, we're going to fail to reject it. These are completely different conclusions. That's why we always have to mention the level of significance that we're using. Okay, so with that in mind, let's try one of these problems. And the problems are going to be very similar to 8.1. The only difference is now we're not going to know sigma in most cases, so we're just going to use the student's t instead of standard normal. So let's take a look at number 20. And number 20 says, let's see, this is on page 468, number 20. They give us some data about Honolulu. And it says, USA Today reported that the state with the longest mean lifespan is Hawaii, where the population mean lifespan is 77 years. Which seems totally unfair because they already have the most awesome weather. And now they also have the longest mean lifespan. It says a random sample of 20 obituary notices in the Honolulu Advertiser gave the following information about lifespan in years of Honolulu residents. So they've got 20 data points here. And if you look, they tell us they've got, if you use a calculator with mean and standard deviation keys, they give us this. So from our sample, got 20 data points in the sample, and they say that the mean of the sample is 71.4 years. Standard deviation is 20.65 years. And they tell us also that the belief is that the mean lifespan in Honolulu is 77 years. Now notice what they don't give us. Unlike section 8.1, they did not give us sigma, right? They didn't give us sigma. We don't know anything about sigma this time. It's a bad drawing with sigma. Remembers that Greek letter that looks like that. But anyway, they didn't give that to us. So we're going to have to use, instead of the population standard deviation, which we don't know, we're going to use the sample standard deviation. So that's the difference. So you notice in the reading it says, assuming that lifespan in Honolulu is approximately normally distributed, which is the key because look at our sample size, we've only got 20. But they tell us that the X distribution, right, the distribution that we're sampling from, has a normal distribution. So we've got, just like 8.1, there's a bunch of things they want us to do, A through E, and those directions start on page 465 at the bottom, and they go up to the top of 466. But it's the same kind of things from 8.1. So we've got things like part A, which says, state what is the level of significance, state the null and alternate hypotheses. Well, level of significance they give us in the problem, 0.05. And then the null hypothesis is that the mean equals 77 years. The alternate, to see that, if you look at the last line in problem number 20, the second to last line, it says, does this information indicate that the population mean lifespan for Honolulu residents is less than 77 years? Less than. So this is going to be mu is less than 77 years, right? Which means because it's pointing here, it's going to be a left-tailed test. So I'm going to just make a quick note of that. It's left-tailed because it's a less than sign. It's a less than sign, which means we're going to be over in the left tail of the student's t distribution. So part B says, let's see, what does part B say? It says, check the requirements. What sampling distribution will you use? Explain the rationale for your choice and compute the appropriate sampling distribution value of the sample test statistic. Okay, well, we are going to use students T distribution with degrees of freedom. If you remember from chapter 7, degrees of freedom of students T is always n minus 1, which will be 19 in this case. 19 degrees of freedom because the sample size was 20. So degrees of freedom is 19. And why can we do this? Because they tell us that the X distribution, right, which is the age of residents of Honolulu, is normally distributed. So X distribution is normal, right, meaning normally distributed. And sigma is unknown. So had they given us sigma, had they given us this information, we would have been using standard normal. But because sigma is unknown, we have to use students T. So with students T, we need to figure out our T-score. So we've got our formula for students T. And just kind of remember, we have to be a little careful here. And so when we plug in the values, we get 71.4 minus 77 over 20.65 divided by the square root. Now I want to be careful here. There's an easy mistake to make. Whenever you use students T, it's really easy to put in degrees of freedom here. But look at the formula, n, 20, right? There's 20 and is the sample size, so put a 20 in here. And then again, make sure you get order of operations right and make sure you divide. This is divide here. And if you do that, we should get negative 1.213. So part C says find or estimate the p-value. Okay, so part C, we want to find the p-value. Well, there's two ways to do this. We can use a table. We can use a student's T table, but when you use a table, we're only going to be able to get an interval of values. We can't figure out exactly what the p-value is. We can just get an interval of values. And this is part of the reason why if you just have a table, we would use what's called the critical region method, which we don't use. We're going to be able to get the value itself by using the calculator. So what we need to do is, if you're going to use a table, I've got students T table here. If you're using a table to do this, you want to look at our T value here and ignore the negative. If you use the p-value, or to find the p-value using the table, ignore the negative. I'll show you how to do it with the table real quick, but then I'll show you the way we'll do it on the calculator. So if you want to use the table, ignore the negative and look under 19 degrees of freedom, and we want to look for the number 1.213 or something close. So you come over to the table under 19 degrees of freedom, and the number 1.213 is right between these two numbers, between 1.187, 1.328. So if you look straight up from those two numbers to this top number that says one tail area, well, all of these numbers in these first two rows here are p-values. So one tail, which is what we are, we're in the left tail, right? We're over here in the left tail. So for one tail areas, right tail or left tail, you're on the one tail area. If you're using a two tail test, then you use the second row. But we are in the one tail area, so under 19 degrees of freedom, the number that we need, our t value, ignoring the negative, is 1.213, which is between 1.187 and 1.328. So if you look up here at the table, that means our p-value is between these two numbers. So if we use the table, all we can say is our p-value is between 0.100 and 0.125. So that's how you do it using the table. So let me get this out of the way here. So if we're going to use a table, this is what we can say. With the table, what we can say is our p-value is somewhere between here. And with the table, that's the best we can do. So we can get an interval of values. But what we want to do, we can do better than this. We can actually get a value, get a number. And so we can get a lot more precision if we have the calculator. So using the calculator, we have to go to, it's going to be very similar to what we did before when we were finding the p-value using z-scores. So remember on the calculator we used normal CDF? Well, this time we're going to use something just like it, but it's called TCDF. So on the calculator, to get there, you go to the same place you would for normal CDF. You go to the distribution. So on the calculator, we would hit the second button. So we hit second, and then you hit vars, right? Second vars, which gets you the distribution menu. So you go second vars on the calculator, and then you go down to before we would look at normal CDF. Now we go down to TCDF. So we want to go to TCDF. It's just like normal CDF. Remember, we don't want TPDF, we want TCDF, just like normal CDF, but now it's TCDF. So if you select TCDF, then it depends on what software you have. Some of you, when you press TCDF, would just see TCDF parenthesis, and others, just like before, we saw this in class, you'll get like lower, upper, degrees of freedom, paste. So some of you will see this, and some of you will just see TCDF. All right, so it works just like normal CDF. So we are looking at, we've got a left tail test, because really what we're doing, let me add something to this, and add this in red up here. The p-value really is this. We're really finding the probability that X bar could be less than or equal to 71.4, which is equal to the probability that T is less than or equal to negative 1.213, right? Because this is our t-score that we got. So it's just like before when we would use normal CDF. So if you think of it the same way as what we did before, it's just we're over in the left tail area. You can actually see it right here on this graph. We're over here, right? So just like when you use normal CDF, we could think of this as negative 10 to 10, because a z-score of negative 10 is extremely unusual. Well, a t-score of negative 10 also is unusual. So in theory, this tail goes to negative infinity, but as far as our calculator is concerned, negative 10 works. So depending on what kind of version of software you have, over here you could have like the lower would be negative 10. If you have this version, you put negative 10 here. The upper here is negative 1.213. If you have this version, it's negative 1.213. Degrees of freedom, 19. So here's the difference. When you use TCDF, we had to put the degrees of freedom in here. And then here you would just paste that to the screen, and then you would get this. Then we would both have this. So the difference is when we're using a t-score, remember we need degrees of freedom. So we have lower bound, upper bound, degrees of freedom. So this is a new command, but it's somewhat familiar because, it should be familiar because it's a lot like normal CDF. And the only difference is we are finding the area under the student's t-curve instead of the normal distribution curve. So we're over here. So if we punch that in the calculator, and if we use this command right here and punch this in, what we get is roughly 0.120 is our p-value. So we can see from the table, it told us it was in this interval, right? When we used the table, we said, the table told us, well, I don't know exactly what the p-value is, but it's between these two numbers. When we use the calculator, we get more precision. We say, here is the p-value. So this is the only time I'll really talk about using the table, because we don't really need to use the tables anymore, but you can use it that way. But if you use the calculator, just use TCDF. It works just like normal CDF, lower bound, upper bound. We just also have degrees of freedom. And we can treat infinity, we can punch negative infinity as negative 10, and we can use positive 10 for positive infinity if we're doing a right tail test, if we're over here on the right. So then basically we're ready to go. We're ready to look at our conclusion. So part D says, based on your answers in parts A to C, will you reject or fail to reject the null hypothesis? Are the data statistically significant at level alpha? Well, remember, if we reject the null hypothesis, then we say, yes, the data are statistically significant. So let's take a look at part D. So for part D, we say our p-value, always, just like before, we're going to compare our p-value to alpha, 0.12. And alpha, in this case, we had a 0.05 level of significance. So we compare these two. We say, okay, here's our p-value, 0.12, it is greater than alpha. So if the p-value is greater than alpha, that means that we fail to reject H naught. Right, we fail to reject H naught. Does that mean we proved that it's true? No, we just are saying, all we're saying is the evidence is not strong enough. Based on our sample, the evidence is not strong enough to reject the null hypothesis. And a lot of times, there's a lot of expensive and big changes that would come if you did reject it. So for something like this could have implications for Social Security, right? If Social Security is based on a certain lifespan, and all of a sudden you find out that, hey, the lifespan is actually different from what we're thinking, that could have enormous implications for how benefits are distributed. So that's why these things are set fairly low, typically 0.05 or 0.01, because you don't want to just change these easily, right? You want there to be strong evidence before you start changing things. So even though you look at this, and this is basically saying that there's only a 12% chance. There's only a 12%. This is our probability. Remember, p-value is probability. The probability that we would get a sample like we did, given that the null hypothesis is true, is only 12%. So you might say, well, that's kind of low. But we want to make sure that before we start changing things, we get a really unusual sample. So 12% might be unusual, but not unusual enough for us to be ready to reject what we assume to be true, right? So our line in the sand is 5%. We basically, before we even started collecting data, we said, okay, we're going with a 5% level of significance. So we're going to look at our sample and calculate the probability we would get the sample like we did, given that the null hypothesis is true. And if we get something that has a 5% or less probability of happening, we're going to reject the null hypothesis. Well, we got a 12%. Our sample had a 12% chance of happening, given that the null hypothesis is true, and that's not enough. So we're going to fail to reject H naught. Remember, we're not proving it's true. We're saying at this time, based on the sample that we got, we're just going to stick with the null hypothesis. This sample wasn't strong enough to make us reject the null hypothesis. So to answer the book's question, we would say the data are not statistically significant. I don't typically ask about that, but the book always says that. So we failed to reject H naught, which is saying that the data are not statistically significant. And then that brings us to the part where we typically struggle the most, which is the conclusion. And what I'm going to do is I'm going to stick to the same format as always. So I'll always conclude these Chapter 8 problems the same way. So I'm going to say at the 5% level of significance, so we always have to mention alpha, because as we saw, if the p-value had been like 0.03, then we'll get a totally different conclusion depending on whether alpha is 0.05 or 0.01. So we have to mention alpha. So we say at the 5% level of significance, the sample data, or in other words, the evidence, right? So you can say that either way. You can just say the sample data, or some people just say the evidence. Remember, our evidence is that sample of data. So the sample data do not suggest, and I'm just going to say H1. So I'm going to say H1, but in words. I can't just say H1. But looking at H1, H1 says that the mean is less than 77 years. So I'm going to write it that the way the book says it. If you look at the question the book asks on number 20, it says, does this information indicate that the population mean lifespan for Honolulu residents is less than 77 years? And I'm just going to say, so that's basically H1. I'm going to say the data do not suggest that, right? The data do not suggest H1. So I'm going to say the data do not suggest that the population mean lifespan, in other words, that's mu, right? The population mean for Honolulu residents is less than 77 years. If you break this into parts, you can see same as before. At the alpha level significance, you just mentioned that. And then we say something like the sample data. And remember that our book always interprets the conclusion in terms of H1, which you don't have to. Since we failed to reject H0, you know what I could say right here? I could say at the 5% level of significance, the sample data suggest H0, right? Because we're not rejecting H0. So I could just say the sample data suggest that the population mean lifespan for Honolulu residents is 77 years. So you could say that too. I would say it's probably not done as much because, again, it sort of sounds like you believe it's true, like almost like you're proving something. So what we just say is at the 5% level of significance, the sample data do not suggest H1. And I just write H1 in words, right? So you can do that with all of those problems. The wording gives us the most problem. So practice those. This format right here works on all of them. And just remember what the p-value is. The p-value, P stands for probability. It's the probability of obtaining a sample test statistic, like that sample mean. That test statistic was X bar, as far away from mu, or even farther away from mu, than the given test statistic, given that H0 is true. So it's the probability of getting that sample that we got, or something even more extreme, even younger, right? More to the left in the tail, given that the null hypothesis is true. So try this section out, 8.2. It's very similar to 8.1, but we're using t-scores instead of z-scores. And let me know if you have any questions.